Okay, we're going to start with the ideal system we talked about when we talked about the ideal Rankine cycle. Okay, in the fact that the boiler pressure is at 1600 psi and the condenser pressure is at 1 psi. That means P4 is 1 psi. I need to drop that in there. So, right? And then I've got a reheat in here. And that occurs, well, it goes down to a saturated vapor at state 2. Okay? So I know the same states as before, and I'll let you go back and watch those videos if you want to see how to do those. 1, 5, and 6 we've already really calculated, right? 1 and 5 are given to us. Again, at this point we've got 1 psi saturated liquid. State 1 was given to us 1600 psi and 1100 degrees Fahrenheit. Okay, and then doing the pump, it's a isentropic pump. So again, VdP, V delta P equals delta H. That's where I get H6 from. Now the differences in here is this reheat, which is basically state 2, 3, and 4. So going from state 1 to 2 is passing through an isentropic turbine, meaning that S2 equals S1. So that's going to be 1.6315. So here's what I've got. I know I have a saturated vapor, okay, at an entropy of 1.63. So I'm going to go into my water table. I know I'm saturated vapor, so really I'm just going to scroll down, okay, until, and I'll just do it for pressure, until I hit 1.63 for saturated vapor. So I scroll down, and you can see 1.63 is going to be in this range right here. Okay, basically between 70 and 75. Okay, in actuality, when I do my interpolation, it's 70.5 psi. Okay, and that corresponds to an enthalpy of 1181.1. Okay, so that's where I am at state 2. Again, I know I'm at saturated vapor at 1.6315 entropy. So my pressure at this point is pressure 2, again, is 70.5, and my H2 is equal to 1181.1. And again, that's because I know my entropy and I know my quality. Any two properties set my state. Now, going to state 3, again, I know I'm at 70.5 because the pressure is constant through a heat exchanger, and it tells me that the temperature is 1,000 degrees Fahrenheit. So I go, again, 70.5. Oh, this will be superheated. So I come over here. Okay, I'm going to have to do some interpolation between, here's 60, here's 80, here's 1,000. I'm more or less halfway between here. I'm going to need both my enthalpy and my entropy because, again, I have another isentropic process here. So doing the interpolation here, I get 1532.9 and 1.96 for my H and my S values here. Okay, so come back over here again. My H value here at state 3 is 1532.9, and my S value after I do my interpolation is 1.9605. Now, going through the rest of the turbine, that means S4 is equal to S3, is also 1.9605, and I know I'm at 1 psi. So I go back into my table, I go to my 1 psi, and I'm looking for 1.96. So at 1 psi, my entropy is between 0.13 and 1.97, so I'm just barely below saturation. So I'm going to have a very, very high quality, and that enthalpy will actually work out to be 1095 when I do the interpolation here. Again, very, very close to the 1105 that is saturated vapor at 1 psi. And I'm just below that because, again, I'm just below the 1.97 at 1.96. So I actually get 1095.9, and that sets my states. Again, I set that because I know P and S, any two properties set my system, or my state. And I get 1095.9. So again, it's the same process using isentropic and constant pressure processes to figure that out. Now I have all of my H values, and I can just figure out what it is that I'm trying to find. So the net power developed is the work of the cycle. Again, I know my mass flow rate. That was given in the original problem. This time I have two turbines that I have to deal with. So it's going to be H1 minus H2, that's the first turbine, plus the second turbine, which is going to be 3 and 4. So that'll be H3 minus H4. And then I have to subtract off my pump, just like I did before, which is going to be H6 minus H5. So again, turbine plus turbine minus pump, right? Because I've got two-stage turbine and a single pump here. When I do that, I get the answer 1.12 times 10 to the 9th BTU per hour. If you remember from the previous problem, my work of the cycle is actually 8.8 times 10 to the 8th. So I have an increase in my cycle, the work of my cycle, which is a good thing. I'm getting more work, more power developed with this reheat going on. Now, there's a trade-off because I also have more heat here. So let's check the efficiency, which is, again, the work of the cycle, which I just calculated, over Q in, where Q in is now, I've got two of them, so it's going to be that mass flow rate times basically 6 to 1, so that's H1 minus H6, plus 2 to 3, which is going to be H3 minus H2. Okay, so I've got two heat additions here, two works, and one workout. Okay, when I plug in all of that, I get an efficiency of 43.8%. If you remember from the previous problem, it was 42.9, so it's a slight increase in our efficiency as well as a slight increase in our work output, which is a good thing. So that's how reheat, plus the fact that at state 4 I was very near, I was at 90+% quality, so that higher quality leads to less erosion in the turbine blades.